All right, so continuity. Loosely speaking, a function is continuous on an interval if you can draw the function without taking your pencil off the paper. That would be a very simple definition of what it means for a function to be continuous. So if you look at that first one,
Excuse the interruption. Nick St. Cyr.
we look at that first function. Could I draw that whole thing without taking my pencil off the paper? This first graph here. What does this little circle here mean? It means there's no point there. So if I were to actually draw this, I would have to come along here. Then I would have to take my pen off the paper and then put it back on and continue drawing. So is this function continuous everywhere here? No, right here we've got a problem. There's a hole in the graph there. It's not continuous. Here's another example. Is this a continuous function? No, I would be going along here. We've got a solid dot there, but then I would have to take my pen off the paper, come down here, and carry on. That graph is not continuous. We have a problem right here. On this one, this third one, is this a continuous function? Could I draw this whole thing without taking my pen off the paper? No, we're going to have a problem right in here, right? So you'd have to take your pen off the paper, you'd have to put a dot there, then you'd have to take it off again and continue on drawing here. So right along here at x equals 0, problem. And on this last one here, continuous? No, again a problem. You'd come along here, you'd have to take your pen off the paper, come down here, put a little dot, come back here, and continue drawing the graph again. So there's 4 different scenarios where a function is not continuous. But we need a proper definition. So let's consider this one here. For a function to be continuous at a point C, the following conditions must be true. So this is a really important term. If you are ever asked to prove whether a function is continuous or prove whether it's discontinuous, these are the 3 truths that must exist if a function is going to be continuous. Number 1, f of c needs to be defined. That means we need to have a y value at that point. Number 2, the limit at that point needs to exist. That means we have to be able to approach from the left and approach from the right, and the approaching values are the same. And then the third condition, which actually summarizes really the whole thing, the limit, when you approach c from the left and the right, that limit must equal the actual function value, f of c. Let's go back and let's look at those 3 graphs, or 4 graphs. In that first one there, and let's call this point C. Number 1 says the function value has to exist. Do we have a y value when x is c in this graph? No, we do not. F of c is undefined. So we would say this graph number 1 is not continuous because f of c does not exist. Condition number 1 did not satisfy. Looking at number 2, let's call this one graph number 2. Is f of c defined? Let's make this point C. Do we have a y value at c? Yep, right here. The second thing that needs to happen is, does the limit exist? No. When I approach from the left and I approach from the right, I'm getting 2 different values. So here, the limit does not exist. Okay, so that was number 2 didn't hold true. Looking at graph number 3, does f of c exist? So yeah, good. Let's make these values c. Yes, right here. Does the limit exist? No. When I approach from the left, it's going to negative infinity. When I approach from the right, it's going positive infinity. So here again, limit does not exist. I'm looking finally at graph number 4. Does f of c exist? Yes. Good. Does a limit exist? No. Yes, it does. When I approach c from the left and I approach c from the right, we're coming towards the same y value. So the limit exists. Does the limit equal f of c? No. The limit is approaching this y value here. We'll call this y1. F of c is way down here at y2. So the limit and the function value are not equal. Therefore, that function is not continuous. And there's a couple of other terms that we need to talk about. There's this thing called a removable discontinuity and a non-removable discontinuity. So these are just some definitions. Quite simply, a removable discontinuity means that a function will have a removable discontinuity at a point x equals a if the limit exists at the point x equals a, but f of a does not exist, that's wrong, does not exist, I should say does not exist, or is not equal to the limit. So something would be a removable discontinuity if the limit has to exist, but the point does not. So here's an example. And here's another example. So if you look at that first graph, we would say that the limit exists. When we approach from the left and approach from the right, the limit clearly exists there. But f of a does not exist. So if we called that a, there's no y value at a. And in the second example, the limit exists, but it's not equal to the y value at that point. And can you kind of see, basically the graph's intact, except there's a little hole at that point. That's why it's called a removable discontinuity, because it's like someone's taken one point and just removed it from the graph. That's why it's called a removable discontinuity. There's just like a hole missing, and maybe someone's just completely taken the hole out, like this example here, or they've taken the hole out and they've moved it somewhere else. Those are removable discontinuities. A non-removable discontinuity, where are we? Right here. A non-removable discontinuity means that the limit of the function does not exist at that point A. So here would be an example of a non-removable discontinuity. The limit does not exist. So these would be functions where we have big gaps. There's a gap in the function. The function jumps from one place. There's another word to define it. It jumps. Jumps down and starts again. But the precise definition would be that the limit does not exist. So we look at three examples here, and the question is simply, are the following functions continuous at the point x equals 3? Well, for something to be continuous, we need to find out what is f of c, what is the limit at c, in this case at x equals 3, and are they equal? Those are the three things that would make the function continuous at that point. So if we look at this one, the first thing we've got to do is find out what is f of 3. F of 3, if I try to substitute 3 in for x in this function, I'm going to get 9 minus 9, which is 0, over 3 minus 3, which is 0. We cannot divide by 0, so f of 3 does not exist. Is it continuous? No. We can stop there, because as soon as one of these criteria doesn't work, we don't even need to evaluate the limit. The question is just saying, is it continuous? Step 1 did not hold true, so this is not continuous at x equals 3. Let's look at this other function. So this is a piecewise function, g of x. We have our original function, x squared minus 9 over x minus 3, and we're going to use that function for all values except x equals 3. If we have x equals 3, we're going to say the y value is 4. So let's look at criteria number 1. It was to figure out what is f of 3. F of 3 is 4. That's what it's saying right here. When x is 3, y, g of x is 4. So that's good. Number part 1 is good. Let's look at step number 2. What is the limit as x approaches 3? Now when we do this, we need to look at this function, because this is the graph that we would be using as x approaches 3. X squared minus 9 over x minus 3. And how are we going to evaluate this limit? This is what you were suggesting, Olivia, right? Do what? Factor it. Yeah, so x squared minus 9, that's a difference of squares. I'm going to factor that to x minus 3, x plus 3 over x minus 3. And now these factors will cancel out. So we have the limit as x approaches 3 of x plus 3, which is 6. So that's fantastic. The limit exists, and it's 6. Criteria number 3 was that f of 3 needed to equal the limit. Well, what was f of 3? 4. And what was the limit? 6. That's not true. So the limit, sorry, not the limit. Go away. Thank you. This function is not continuous at x equals 3 because the function did not equal the limit. Whoop. Why does it do that? Let's look at this function, h of x. I think I used f back there. That was a mistake, wasn't it? I should have had g's on these because we were talking about a g function. This function was called g of x, not f of x. This one's called h of x. H of 3 in this case now is 6. The limit as x approaches 3 was, it's the same function, so we won't go through all the song and dance. We found that that limit was 6 from the one before. And criteria 3 was that h of 3 needed to equal the limit. And indeed, 6 is 6. Yes? Hooray! 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 All 3 criteria are true. This function is continuous now at x equals 3. So here's just something of note. Certain functions, such as polynomials, are continuous everywhere, since for all values of x, the limit of the function at any point would always be equal to its function value. Polynomials, remember, are those equations that are like x cubed minus 2x squared plus 7, those sorts of things. And when you graph them, they always have these wavy lines. So polynomial functions are always continuous. The limit will always equal the function value. There's never any gaps or jumps or those sorts of things. Polynomial is continuous everywhere. Rational functions, these are the functions where it's fractions, like x squared minus 3 over x plus 1. That would be a rational function. We have a variable in the denominator. They would be continuous everywhere except for the value or values of x that make the denominator 0. Because those are the places where the function would not be defined. Step 1 of our proof, f of c existing, would not happen for in this example when x equals minus 1. If I put negative 1 in here for x, I get 0 in the denominator. This function would not be continuous at that point because the function value doesn't exist. But for all other values of x, this function would be continuous. So rational functions, they're continuous everywhere except for the values of x that make the denominator 0. Why? Because they're undefined at that value. We can also talk about functions being continuous from the left or from the right. So very simply, we would say a function would be continuous from the left if the following condition is true. A function would be continuous from the left if the limit as x approaches a from the left is equal to the function at that point. And a function is continuous from the right if the following condition is true, when the limit as x approaches a from the right side of the function equals f of a. So let's look at this graph here. And let's say for the purposes here that this is a, and we want to look at, is this function continuous from the right? We can't even approach it from the left, so we couldn't say that the function is continuous from the left because there is no left of a. The function starts at a. So for a function to be continuous from the right, we'd have to look at, does the limit as x approaches a of f of x equal f of a? So when I approach a from the right, is it the same value as my function value at a? Yes or no? Yes. The limit from the right is coming down towards this value here, which is the same as my function value. So for this example, the function would be continuous from the right at a. If we pretended now that this was point A, let's see if this function is continuous from the left at this point. Is the limit as x approaches a from the left equal to f of a? No. So here would be an example where this function is not continuous from the left, because as I approach the left, I'm coming up to a different y value than the actual y value is. Now a theorem comes out of this, continuity and so on. Let's read it. If f is a continuous function, so we need a continuous function on a closed interval a to b. So here's point A, here's point B. It's continuous clearly here on that closed interval a to b. If x is a, here is the y value, so we'll call that f of a. That's the y value when x is a. Here's the x value of b, and here's its y value, f of b. Okay, that's whatever that y value is, that's where it is. K is going to be some y value between f of a and f of b. So let's just say it's right here. There's point K. So K is a y value between f of a and f of b. Then, this theorem says there has to be at least one number x between a and b, somewhere in that interval, such that f of x equals k. Now, you don't have to overthink this theorem. It's a very simple theorem. What it means is, if this function's continuous and it goes from a y value, let's just say this is 3, all the way up here to a y value that is 9, then somewhere between here and here, it must hit some place where there's a y value, say, of 7. Because if your graph is going all the way from 3 to 9, there has to be somewhere in between there where you're going to hit a 7. It's like this. Some of you will have been on the Grouse Mountain sky ride. Does anybody know exactly how long it takes to get to the top?
How fast they're running.
Oh. Let's say it was a 7-minute ride. No, let's keep it simple. Let's say it's a 10-minute ride from the bottom to the top on the Grouse Mountain sky ride. Let's say you get on the bottom and it's at 300 meters is your elevation when you get on the bottom. And you know that you get off the top, it's at 1,000 meters. Then it's like saying this. The intermediate value theorem says this. There will be some place between 0 and 10 minutes on your ride up where you will hit an elevation of 700 meters. Would that not be true? You'd have to. You're going from 300 meters to 1,000 meters. Somewhere between there and there, you're going to hit 700 meters. It's not like the sky ride all of a sudden, in no time, jumps and misses that 700 meter line. That's the same as this intermediate value theorem. If this is a continuous function, and we are going from a to b on our x-axis and f of a to f of b on our y-axis, then somewhere in between these two y values, or if you like, this elevation, there must be a x value between A and B. There would have to be. Because it's a continuous function. There's no way you could go from this point to this point without crossing that line of 7. You might cross it more than once. The graph might do something like that. But there's going to be at least one place where you will hit, in this little example here, 7. Or if you think of the sky ride, 700 meters. Let's say we had a situation like this. Let's say at this point right here, we have an x value of 2, and let's say the y value is right up here at, let's just call this 1, 2, 3. And let's say over here, there's an x value of 5, and let's say there's a y value down here of minus 1. So we have a point right here. So this is the point 2, 3, and this is the point 5, minus 1. Then the intermediate value theorem would tell us that if this would be a continuous function, then there must be some place between 2 and 5 on our x-axis where we will have a y value of 0. Correct? How are you going to get from this point to this point without crossing the x-axis if it's continuous? You would have to, agree? You would have to, at least somewhere in here, we will have to cross the x-axis. So if you know your function's continuous, and you know at one point you have a positive y value, and another point you have a negative y value, then you have located a root. Somewhere between those two x values, in our case 2 and 5, there will be a root. You don't really know where it is, but you know it's going to be somewhere between those two points. So somewhere between an x value of 2 and an x value of 5, we will have a place where the y value is 0, and that'll be a root. So that's the intermediate value theorem.